Right now, as you are reading these lines, there is a frame drifting through space that no one can ever capture again. It is not an ordinary frame, but a photograph of the entire home of the human species, condensed into 0.12 of a pixel. No technology today is capable of recreating it. No spacecraft is in the right position to take it again. No plan of NASA or any space agency on Earth will ever take it again. And no engineer can still issue the command to shoot, even if all of humanity were to kneel and beg. The photograph was taken before the internet existed, before most of the people watching this video were born, with a Vidicon lens from the 1970s, an era when televisions still used cathode rays to scan each line of pixels one by one. The entire historic moment lasted only 34 minutes. 34 minutes, shorter than one television episode, less than the time it takes to commute home from work, less than an average gym session. That was the total time the eyes of Voyager 1 remained open after it pressed the shutter on Earth from a distance of 6 billion kilometers. And that 13-year-old 4-watt machine launched into space with the hope of surviving only a few short years in the final 34 minutes of its life as a photographer, created an image that will outlast the civilizations on Earth, outlast the oceans, and perhaps even outlast Earth itself. Researchers today do not use words like beautiful or historic when they speak of this photograph. They use words like fate, unreproducible, and once in the history of the human species. This is the story of the last image the eyes of Voyager 1 ever saw. And this is the part the headlines never tell you. Not only the 8-year internal struggle inside NASA that no one has spoken of, 6 rejections, 6 times a man named Carl Sagan had his proposal shelved, but the 34 fateful minutes of February 14th, 1990, Valentine's Day, when the camera was finally allowed to look home, and a permanent decision signed 36 years ago that made this photograph impossible to take again. Not now, not ever. Stay with me, because by the time this story ends, you will never look at Earth or any photograph of it the same way again. Subscribe right now if you want to hear more stories like this, because we are only just beginning. The beginning of this story took place in an office in Pasadena, California in early 1981. A 46-year-old man named Carl Sagan sat in that office with an idea in his head. The idea was simple and modest. Before the cameras of Voyager 1 were shut down to conserve power for the long journey ahead, turn the lens around one time, take a photograph of Earth from the greatest distance human beings had ever photographed it. Not to collect data, not to discover anything new, just a point of view, a moment for humanity to see itself from the outer edge of the solar system. Sagan wrote the proposal and sent it to the Voyager Project Committee. NASA would reply in a few weeks. It would be a short meeting, a polite rejection, a piece of paper into a drawer, then silence. What actually happened was one of the longest internal battles in the history of JPL, and most people have no idea how long it lasted. The first proposal was rejected, but Sagan did not withdraw. He rewrote it in 1982, rejected, rewrote it in 1983, rejected. That same year, a younger member of the imaging team named Carolyn Porco, unaware that Sagan had proposed the same thing 2 years earlier, submitted a nearly identical proposal, also rejected. The fourth proposal in 1984, the fifth in 1985, once every year, the same answer. By the time the 1980s entered their final years, Sagan was 53 and writing the sixth proposal. Voyager 1 was then at a distance of 40 astronomical units, farther than Pluto, farther than any artificial object in human history at that time. And it was still transmitting, still sending its faint signal across the ever-growing void. The cameras still working, the lenses still intact, the tape recorder still ready, all of it still waiting for a moment no one had yet allowed to happen. Then something occurred that suddenly reversed the entire struggle. On August 25, 1989, Voyager 2 flew past Neptune. The planetary science program of both spacecraft officially ended. If you do not yet understand why this detail changed everything, here is a way to picture it. For 8 years, the reasons NASA rejected Sagan always had 2 layers. The first layer was technical. Pointing the camera near the sun could burn out the Vidicon, and no one wanted to risk destroying the camera while Voyager 1 might still have other scientific missions later. The second layer was political. Every hour of camera operation had to be justified by clear scientific value, and a photograph with no data did not meet the standard to compete with pending scientific targets. Everything inside that political layer belonged to the program. Everything outside it, including a picture taken simply to look, had no place at all. But after August 25th, 89, that political layer vanished. Not metaphorically, not technically, it truly vanished. Physically, concretely, no more planets waiting. No more scientific targets to prioritize. The barrier Sagan had fought for 8 years to break simply no longer existed. Richard Truly, former Navy admiral, the NASA administrator who had just taken office that May, heard the family portrait proposal for the 6th time. No drama. No big meeting, just a signature. Approved. After 8 years, 6 rejections, enough time for a child born the same year as the first proposal to have entered second grade, but Truly's signature could not change one thing. The schedule to shut down Voyager 1's cameras remained fixed. Sagan had only a few months of window. After that, the idea would die forever. And then JPL began to run. What was his idea? Voyager 1 should turn its lens around, take one photograph of Earth from that distance. That was the entire idea. One sentence, 9 words. Not a complex scientific program, not an experiment requiring special calibration, not a mission needing new funding, just turn the camera around, press the button, save the image. Sagan himself knew what was wrong with his idea. In the first presentation to the Voyager project managers in the spring of 1981, he said it straight, without trying to hide it. This photograph will give us no significant scientific data. Earth will be only a point of light. Period. So why take it? Because 13 years earlier, on December 24th, 1968, Christmas Eve, astronaut Bill Anders on Apollo 8, while orbiting the moon, held a Hasselblad camera, looked through the small window, and pressed the shutter. Earth rose above the lunar horizon, blue, round, alone, suspended in the void. The photograph later called Earthrise. It had no scientific value whatsoever. It measured no temperature, discovered no new planet, confirmed no physical theory, yet it became the symbol of the global environmental movement, and changed the way human beings looked at their planet in a way no scientific lecture ever could. Sagan wanted to create a moment like that, but at a distance 100,000 times greater. The answer came back a few weeks later. Short, polite, rejection. 2 reasons were given. The first was technical. The Vidicon lens of Voyager 1 was 1970s technology, extremely sensitive, extremely fragile, designed to operate in the cold darkness of deep space rather than endure strong light. Photographing Earth from 6 billion kilometers required pointing the camera in a direction near the sun. Sunlight, even weakened at that distance, was still strong enough to risk burning the Vidicon sensor. Voyager 1 might still have many scientific missions later. They could not risk destroying the camera for a photograph that yielded no data. The second was resources. The Deep Space Network antennas were tightly scheduled for dozens of missions at once. Engineers had heavy workloads preparing for Voyager 2's Uranus encounter in 1986. Processing data just returned from Saturn, racing against dozens of other deadlines. This photograph, if it brought no scientific data, did not deserve priority time. The proposal was shelved. Sagan returned to his office with a piece of paper in his hand. This is where the story is usually stopped. People withdraw the proposal, people are disappointed, people give up. But it did not stop. But it did not stop. In early 1982, Sagan wrote the second proposal. The same argument, the same answer. Rejection. 1983, the third time. 1984, the fourth, 1985, the fifth, once every year. The same answer. There is a little mentioned historical detail from that period. In late 1983, Carolyn Porco, another young member of the Voyager imaging team, who would later become leader of the Cassini imaging team, independently put forward a similar proposal. She proposed that Voyager 1 turn its lens around and photograph Earth. She did not know Sagan had put forward the identical idea 2 years earlier. She thought it was her own idea. Her proposal was also rejected. 2 people, 3 years apart, the same idea, the same wall. Meanwhile, Sagan was not only writing proposals, he was writing books, producing documentaries with Anne Druin, designing the golden record attached to both Voyagers. Everything he touched was a way of telling a long story about the place human beings live in the universe. But the final piece needed to complete that story was still not approved, and the spacecraft outside was not standing still waiting. After flying past Saturn at the end of 1980, Voyager 1's trajectory had left the ecliptic plane, the plane in which all the planets of the solar system orbit the Sun. It climbed outward, into a unique position in history, far enough, high enough, tilted enough to look down on the entire solar system in a single frame. But the only spacecraft that had ever been capable of taking that photograph was drifting farther away every second. In the hallways of JPL, people began to look at Sagan with skeptical eyes. He was wasting time on a photograph that yielded no data, while Voyager 2 was preparing for the Uranus encounter in 1986, while mountains of Saturn data remained unprocessed. Why not focus on what actually mattered? But Sagan had an ally. Bradford A. Smith, head of the imaging team, the principal investigator for the ISS instrument. Smith had stood with Sagan from the first proposal. He provided technical support, scheduling support, internal political support, but project leadership still would not turn. Then in 1987, a door cracked open. NASA decided to use Voyager 1's camera to confirm the dust bands that IRAS had discovered in 1983. The camera was switched on, the lens opened, the Vidicon warmed up. They photographed. Nothing was detected. 0. Sagan thought the final door would open. The camera had been confirmed, still operational. The technical risk had been checked. Leadership had already invested antenna time in a project that yielded no results. So why not open it further for the family portrait? The answer that came back was still rejection. Sagan wrote the sixth proposal, late 1987, early 1988. The same answer, Sagan was 54, Voyager 1 was farther away every second. Both were running out of time. There is another way to understand why Sagan did not give up, and this is where the story stops feeling technical and begins to feel like something else. Sagan believed, and he had spent his entire career proving this belief, that human beings do not change their behavior only because of science. Human beings change because of perspective, because of a way of seeing. You can give someone every number, every chart, every report, and they will nod and forget within a few days, but give them the right photograph at the right moment, and it can haunt an entire generation. Sagan knew this not from theory. He knew because he had witnessed it with his own eyes. Before Earthrise in 1968, the environmental movement was only the business of scientists writing reports no one read, of a few concerned citizens without a loud voice. It was not present at ordinary family dinner tables. After Earthrise, everything changed within a few months. Earth Day was held for the first time in April 1970, only 16 months after the photograph, with 20 million Americans taking to the streets. The United States Environmental Protection Agency was established that December. The Clean Air Act was passed a few weeks later. A photograph with no scientific value whatsoever had changed the way a civilization saw itself. That was what Sagan wanted to do again. But at a scale no Apollo had reached, because Earthrise still showed Earth as a full, clear, beautiful sphere. In Earthrise, we were still the home. Sagan wanted a different frame. He wanted a frame in which Earth was a speck. A speck so small that anyone looking would have to ask, is that really us? That tiny speck? That is all of human history, all the wars, all the love, all the suffering, all the art, on that speck? This is the part history usually does not tell. The 8-year struggle between Sagan and the Voyager project leadership was not about science, not about budget. This was a struggle between we need to know and we need to feel, between treating the universe as a laboratory and treating the universe as a mirror. For 8 consecutive years, the leadership chose the first side, Sagan chose the second, and neither side would yield. But the clock kept running. On January 1st, 1990, the Voyager interstellar mission officially began. The cameras had to be shut down before that date. If Sagan did not obtain the approval signature within the final few months of 1989, the window would close forever. By 1987, there had been a moment that nearly changed the balance. Then, in 1989, the event that truly changed everything. On August 25th, 1989, an event occurred outside Voyager 1, billions of kilometers away, that changed every calculation inside JPL. Voyager 2, the twin of Voyager 1 launched only 16 days earlier, approached Neptune. It took the first close-up photographs in history of the farthest blue planet, the storms on its surface, the great dark spots swirling like its brother Jupiter, the methane cloud bands drifting through the atmosphere. It photographed Triton, Neptune's largest moon, with its nitrogen ice mountains and the active plumes erupting at the very moment the spacecraft flew past. It sent back data on the magnetic field, on temperature, on the extremely strong winds. Then it flew on, into the dark. That was the last planet in the solar system. After Neptune, there was nothing left to reach. The planetary science program of the Voyagers, both spacecraft, 12 years of research, tens of thousands of photographs, billions of data points, officially ended on the night of August 25th of that year. And with that ending, every reason the Voyager project leadership had used to block Sagan for 8 years also vanished. There were no more planets left to fly to. There was no more scientific priority left to favor. No one could still say the family portrait photograph would take the place of a more important scientific target, because there was no greater scientific target remaining. Richard Truly, former Navy pilot, former astronaut who had flown on Space Shuttle Columbia, the man newly appointed NASA administrator in May of the same year, heard the family portrait proposal for the 6th time a few weeks after the Neptune flyby. No drama, no large argumentative meeting, no long speech by Sagan, just a signature on a piece of paper. Approved. After 8 years, after 6 rejections, after a stretch of time long enough for a child born the same year as the first proposal to have entered 2nd grade. But Truly's signature did not free up time. It only opened a narrow door. Very narrow. Truly had only 3 months. After that, the idea would die forever. Because Voyager 1's cameras had already been scheduled to shut down within those exact few months, no delay possible, no renegotiation, no extra time to request. Every week of running the cameras was every week of power taken away from the instruments that would measure the interstellar environment for the next 30 years. If the family portrait was not taken in February of 1990, never, JPL began to run. Sequence commands were written line by line. Pointing angles were calculated to 1,000th of a degree. Robin Vaughn, a young optical navigation analyst at JPL, used the SPICE toolkit to double-check every camera pointing angle through each frame of the 60-frame mosaic, because if it was off by 1,000th of a degree, the image would miss Earth. Candy Hansen and Carolyn Porco, the same person who had independently proposed the photograph 6 years earlier, now sat together, writing and calculating exposure times for each frame, each filter, each planet, 6 months of preparation, for one photograph that would yield no scientific data. Sagan had waited 8 years for this photograph. Now JPL was waiting for Voyager 1 to warm up a camera that had been asleep for 10 years. February 13th, 1990, 9 o'clock in the evening, Pasadena time. In the mission control room at JPL, a small group of engineers sat in front of the screens waiting. Not a public event, no reporters, no live broadcast, only a sequence of commands written over the past 6 months and a button to send. JPL sent the signal. The signal traveled at the speed of light, taking 5 hours 30 minutes to reach Voyager 1 at a distance of 6 billion kilometers. During those 5 hours 30 minutes, no one in Pasadena could do anything, could not cancel, could not correct, could not call it back. The spacecraft had received nothing yet. It was still flying silently toward interstellar space, unaware that humanity had just sent it the final command to look home. Then the spacecraft received the command. The ISS camera, the Vidicon eyes of Voyager 1, had been asleep since the winter of 1980, 10 continuous years, in the negative 20 degrees Celsius cold of deep space. No heater, no maintenance, no engineer had ever stopped by to check. If the lens had degraded after 10 years, no one knew in advance. There was no way to test. No simulation could accurately predict how the selenium-sulfur Vidicon target would react after a decade of hibernation. There was only the way of switching it on and seeing what happened. 3 hours. That was the time NASA had scheduled to warm the lens. 3 hours to awaken the old eyes, 3 hours for the Vidicon temperature to rise gradually, for the electronics to stabilize, for the camera command subsystem to run through the entire self-check sequence and report that everything was fine. During those 3 hours in Pasadena, no one left the control room. Then the science platform turned. The spacecraft rotated slowly in space, bringing the lens to aim at a chain of small bright points lying just to the right of the constellation Orion. Seen from Earth, that chain of points was only faint stars, hard to notice in the night sky. But at Voyager's distance, 6 billion kilometers out at the edge of the solar system, that chain of points was not distant stars. It was the spacecraft's family. It was the Sun and the planets, seen from outside. Photograph Neptune, photograph Uranus, photograph Saturn, photograph Mars, but Mars was lost in the scattered light of sunlight reflecting inside the lens, leaving only a bright streak where the red planet should have been. Photograph the Sun through the methane absorption filter, the darkest filter the camera had, with a 5,000th of a second exposure, the shortest possible, short enough not to burn the Vidicon. Then Jupiter. Each frame was saved to the onboard tape recorder, bit by bit. In the silent cold of deep space, the spacecraft continued to turn. Then at 4 hours 48 minutes Greenwich Mean Time on February 14th, 1990, Valentine's Day on Earth, while millions of couples were exchanging roses and boxes of chocolate, while almost no one on this planet knew what was happening 6 billion kilometers away, the narrow-angle camera of 1,500 millimeters at f/8.5 opened its shutter for the last time in its mission. 3 filters in succession: violet, blue, green. 3 frames, later combined into a single color image. 3 presses of the button. 3 moments of exposure. In those 3 frames, Earth occupied exactly 0.12 of a pixel. The Vidicon was not burned, the lens remained intact, sunlight was not strong enough to destroy the spacecraft's eyes. But the band of scattered light, the very thing JPL engineers had warned Sagan about for 8 years, appeared in the image. The data was saved to tape. Then the journey home began. The data began its journey home. The Deep Space Network, 3 giant antennas at Goldstone, California, Canberra, Australia, and Madrid, Spain, caught the faint signal across 4 separate communication passes from March to May of 1990. The signal delay at that time was 5 hours 30 minutes one way. One afternoon in May at JPL Pasadena, a woman named Candace Hansen, planetary scientist, experiment representative of the Voyager imaging team, sat alone in her office, door closed, blinds down. The computer displayed the image database just downlinked. She was the first person on Earth to look at the frame that contained Earth. And she did not see Earth. Kind of terrifying, she later recalled, because I didn't see it at first. Because of that band of scattered light, it didn't jump out at me right away. I was afraid we had missed it or exposed it wrong. She zoomed in, adjusted the contrast. Then she saw it, just a small speck, 2 to 3 pixels. In those 2 to 3 pixels lay every city, every war, every piece of music, every cathedral, every marketplace, every tear, every laugh. She sat in silence in the dark office. No one else knew. But this is the part Sagan did not yet know, Hansen did not know, and no one still living that day knew. This is where this photograph differs from every other photograph. The bright band cutting across the image, the band in which Earth sits right in the middle, is not real light. It is an error. At a distance of 6 billion kilometers, the light of the sun was still too strong for a Vidicon lens from the 1970s. When the light hit the lens, part of it reflected between the internal surfaces of the optics, spreading into ghostly bright bands across the sensor. Technically, the phenomenon is called scattered light, lens flare, a defect that the JPL engineers designing the imaging science subsystem in 1976 could not completely eliminate. This was exactly what the engineers had warned Sagan about for 8 continuous years. If you pointed the camera near the sun, the light would create an artifact. Unavoidable. The image would have a streak. That was not an operational error, it was a physical limit of the technology. So the bright streak cutting across the family portrait image is a technical failure, by every definition, warned about in advance. And fate, pure coincidence, pure chance, placed Earth exactly in the middle of that bright streak. Pause for a moment. If Earth, in its orbital position on February 14, 1990, had been somewhere else, if it had been only a few degrees off, it would not have lain inside the scattered light band. It would have been only a small blue speck sunk in darkness, anonymous, faint. No one would have engraved any 4 words on a memorial for it, but Earth was in exactly that position, and the defective bright band was in exactly that streak. 2 things. 1, the billion-year motion of a planet around its parent star. 1, the optical defect of a lens assembled in a workshop in California in 1976 coincided in a moment shorter than a breath, and the photograph became a small blue speck lit by light, like a mote of dust suspended in a sunbeam. This is the part that makes this photograph unlike any other in history. Not that Voyager photographed Earth perfectly. Voyager failed by every technical standard of that era, but that failure is exactly what made the photograph. Sagan would later describe that speck with 4 words. A mote of dust suspended in a sunbeam. A mote of dust suspended in a sunbeam, but that sunbeam was the lens error. That mote of dust was us. And both exist together in that frame only because of the long struggle of one man, one final signature, and a camera that was about never to open its eyes again. So what is in those 60 frames? 60 frames in total, 39 wide-angle, 21 narrow-angle. The sun at the center of the mosaic, seen from Voyager 1 only 1/40th the diameter it appears from Earth, yet still 8 million times brighter than Sirius, the brightest star in our night sky. That is why its light was still strong enough to create that fateful band of scattered light. And the camera that took this entire mosaic, look at it carefully for a moment. The Vidicon tube of Voyager had a diameter of 25 millimeters, magnetic deflection, with a selenium-sulfur target behind a transparent faceplate coated with a thin tin oxide layer. When photons from Earth, after their 5-hour, 30-minute flight, struck the selenium-sulfur target, they freed electrons. The stronger the light, the more electrons. These electrons were drawn toward the faceplate, leaving small gaps on the target, an invisible map of the light that had arrived. Then a cathode at the bottom of the tube fired a beam of electrons at the target to scan. New electrons filled the gaps, producing a changing electric current at each point. That current was the image data. Image size, 800 by 800 pixels, 8-bit grayscale. Each image occupied about 5 million bits, less than half a megabyte by today's standards. Serial number of the narrow-angle camera, SN07. Build date, December 17, 1976, only 8 months before Voyager 1 left the launch pad. Filter wheel, 8 filters per camera, controlled by commands from the ground. 6 planets in hand: Neptune, Uranus, Saturn, Jupiter, Earth, Venus. The farthest selfie in the history of the solar system, but 3 planets were missing. Mercury was too close to the sun to photograph without burning the Vidicon, the same fear the engineers had warned Sagan about for 8 years. Mars was lost in the band of scattered light, the same bright band that became Earth's sunbeam. Only Mars was not lucky enough to lie in the middle of it. Pluto was too small, too far, too dark to detect. The size of Uranus and Neptune in the image, stretched into streaks by the spacecraft's motion during the 15-second exposure. The size of Jupiter and Saturn, large enough to fill one narrow-angle pixel. The size of Earth, 0.12 of a pixel, smaller than a mote of dust. The entire solar system in 60 frames, never photographed before, never photographed again in the following 36 years. Only 3 spacecraft ever capable in principle: Voyager 1, Voyager 2, and New Horizons, but Voyager 1 was the only one that ever did it. 5 hours, 22 minutes Greenwich Mean Time, February 14th, 1990, 34 minutes after the Earth frame was saved to tape. JPL sent the final command to the imaging science subsystem of Voyager 1. Power ran through the Vidicon for the last time. The filter wheel turned to the park position, the lens closed, not to rest. This was a permanent decision. The plan to shut down the cameras had existed long before, to conserve power for the journey into interstellar space. Sagan had only managed to insert one moment before that day. A few months later, JPL carried out the second step, the irreversible step. They erased the ISS control software from the spacecraft's flight data subsystem. The code that allowed JPL to tell the camera what to do was erased from memory, because that memory was needed for the other instruments that would measure the interstellar environment for decades to come. On Earth, the computers that knew how to read Vidicon data were gradually retired. The engineers who knew how to read the files retired. The people who wrote the original code in 1976 retired or died. 3 layers of lock: power, software, and human knowledge. None of the layers can be unlocked again. The pale blue dot photograph, if it had not been taken in that 34-minute window, would never have existed. Not hard to take again, impossible. But the story is not finished. On May 30th, 2024, 34 years after the cameras were permanently shut down, NASA's Planetary Data System released a new dataset. Title: Voyager 1, Restored Cruise Images of Uranus and Neptune. Lead author Daniel Wenkert, together with the JPL team. PDART project number 16, content: conversion of nearly 30,000 binary QEDR files from the old tapes stored at the Multi-Mission Image Processing Laboratory for 4 decades into modern PDS-4 format. Among them 272 previously unpublished Voyager 1 narrow-angle images. The accompanying document, JPL Document D110368, has Appendix E with its own title, The Voyager Family Portrait. The eyes of the spacecraft have closed. But what they saw has still not been fully read. 34 years later, we are still opening each frame. This is the kind of legacy Sagan probably never imagined. He did not believe that 34 years after he was gone, engineers he had never met would still be sitting in the cold rooms of JPL, decoding every byte of the frames he had fought 8 years to allow to be taken. Sagan did not live to see this part. Carl Sagan did not live to see it. On December 20th, 1996, Sagan died at the Fred Hutchinson Cancer Research Center in Seattle of myelodysplasia, a form of bone marrow disorder he had fought for the final 2 years. 62 years old, but he had still managed to do one thing. In 1994, he published the book Pale Blue Dot, A Vision of the Human Future in Space, the photograph on the cover. In the book, there is a passage he recorded in his own voice, the recording now held by the Library of Congress of the United States. Look again at that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives, on a mote of dust suspended in a sunbeam. The mote of dust, 0.12 of a pixel. The sunbeam, the lens error itself. Sagan had won the 8-year battle to obtain a photograph in which the very lens he fought against did not want to allow to be used, had become the star of the image. Today, August of 2026, 36 years later, Voyager 1 is at a distance of 25.5 billion kilometers. Susie Dodd, Voyager project manager, each morning sends, "Good morning, Voyager 1." The answer returns after 46 hours. 36 years later, the spacecraft is still flying. But its eyes closed 34 minutes after that frame, and will never look at us again. Only once in history, only one blue speck in the darkness. That is us.